Hello everyone, welcome back to the course on Trustworthy Machine Learning. In this lecture, we will talk about model stealing and defenses for self-supervised learning. Let's start from the beginning. How do we use the machine learning APIs? Imagine that you have an image and would like to label this image. You can send this image as a query to the ML API, and API responds with the label, in this case being a label of a dog. However, the user who queries the API might be malicious, with a goal of extracting the model behind the API. So the question is, how to steal the model behind the API? It is relatively easy. An adversary has to collect some unlabeled data, and then each of the unlabeled data item is sent as a query to the ML API. The API responds with a low-dimensional outputs, such as labels or softmax scores. Based on these queries and obtained labels, an adversary trains a stolen copy of the victim model. What are the assumptions? So it is enough to have unlabeled natural data even from a different distribution than the victim's training set. The architecture of the stolen model does not have to be the same as the victim's architecture. Additionally, ML APIs expose meta-information about their models, for example, on what data the model was trained, or what is the model architecture. And this is done to provide more trust and transparency for the users. Up to now, we have discussed the supervised learning APIs, where the victim model returns a low-dimensional output such as labels or softmax scores. However, currently, the self-supervised learning emerges as a dominant paradigm behind modern ML APIs. The major paradigm shift is that these large self-supervised models are trained on a big amount of unlabeled data. Despite the fact that SSL emerges as a dominant paradigm behind ML APIs, existing defenses against model stealing for supervised learning are not easily retrofitted to the specific features of self-supervised learning. Let us discuss a bit more the self-supervised learning approach. For a given query, the self-supervised learning returns high-dimensional representations, also called feature vectors, and this is done instead of returning just low-dimensional labels or softmax scores. And these representations are usually a high-dimensional vectors with real values. The dimensionality of these representations is often more than hundreds, usually 1 or 2 thousands. The representations are features extracted from the query, and they can be used for many downstream tasks. For example, let us take the dataset like CIFAR10 with 10 classes of images. We pass this dataset through a self-supervised learning encoder and then obtain useful representations. The representations are used to train only a single classification layer on top of the encoder to classify the images into 10 classes. If you want to obtain even a higher performance, you can also fine-tune a few last layers or even fine-tune the whole encoder to obtain even higher performance on your downstream task. However, the main idea is that SSL encoders can already extract useful features, and then the only task is to train a classifier on top of them. Going from supervised to self-supervised learning is essential. It's essential since representations can be reused on many downstream tasks, and you need a small number of labels to train these downstream tasks. Let us now discuss a few frameworks for self-supervised learning. The first one is SimCLR, also called SimCLR. So the SimCLR framework learns representations by maximizing agreement between differently augmented views of the same sample image, and this is done via contrastive inference laws in the latent space. And we'll discuss also other losses very soon. So the architecture of this SimCLR framework is a Siamese network or Siamese network that contains two encoders with shared weights followed by a projection head. So here we have the representation, the schema for this learning paradigm. So what we observe is that here we have input image X can be, for example, any input image from any dataset. We augment this image with two different augmentations, also called transformations. This is this big tau. We obtain this transformed X to be X I, X sub I, X tilde sub I, and X tilde sub j. And then both of these augmented views of X, they are just called views. They are passed through the encoder F, and then we obtain representations H sub I and respectively H sub j. Once we have the representations, they also go through a so-called projection head. This is usually a small neural network, usually one or two-layer network with some nonlinearity in the middle to obtain these representations Z sub I, and these are also called just projection head outputs. And then we maximize agreement between these two representations. So what we want to achieve is that these two augmented views of the same image, the image in principle should have the same meaning for this both of these views, and then we want these representations for this image to be roughly the same. So during training, these encoders are fed either two augmentations of the same input, which are called positive pairs, or augmentations of different inputs called negative pairs. So you want to imagine actually that these inputs X sub I and X sub j are actually different images, and that actually we don't want to maximize agreement, it's the opposite, we want to minimize the agreement. So the output representations of the encoders are fed into the projection head, whose outputs are used to compute the distance in the latent space. So the positive pairs, so views of the same image, should be close in this latent space, and then negative pairs should be far from each other in the latent space. The encoders and the projection head are trained concurrently. The crucial data augmentation to create positive samples and achieve strong performance is a combination of a random resize crop and color distortion. After training of the SimCLR encoder, the projection head, this G part, is removed, and then we just return F, this encoder part, as the final output from training of the SimCLR encoder. This is an example of the contrastive loss. We generate two augmentations, X sub I and X sub j, for each data point X in the batch. In the representation space, we want these two augmentations from the same image to be close to each other, while the other augmented points are treated as negative pairs that we want to repel from each other in the latent space. This is also expressed in the equation, where sim is the cosine similarity score and tau is the temperature scaling. Similarly as in the mixed match description, we also use this tau to control the temperature, and here in this case, if tau is small, then the loss is dominated by small distances, meaning that the positive pairs play much bigger role than the negative pairs. Otherwise, the loss is dominated by the negative pairs for high temperatures tau. Here is an example of the soft nearest neighbor loss. The code on the left-hand side implements the equation. The output on the right-hand side is what we want to analyze. So we start from a simple distances recorded for the positive pairs, which is simply 1. The distances for the negative pairs are set arbitrarily to 5, 4, 5, 7, just larger distances than for the positive pairs. For the highest temperature of 100, the loss is dominated by the negative pairs. The overall loss is high. On the opposite end of the spectrum, for the very small temperature of 0.1, the loss is dominated by the positive pairs and matches the value for all other pairs. SimSiam is another Siamese network architecture that utilizes contrastive learning like SimCLR, but simplifies the training process and architecture. In SimCLR, negative samples are needed during training to prevent the model from collapsing to a trivial solution, that is to output the same representation for all inputs. And the authors of SimSiam show that negative samples are not necessary. You can just train the encoder without them. And the collapse can be avoided by applying the projection head to only one of the encoders in alternation and preventing the gradient from propagating through the other encoder during training. Here in the schema, we only have positive pairs for image x, namely x sub 1, x sub 2, and we pass them through the same encoder, but only one of them, the x sub 1, is further passed through the projection head. Then we only update the projection weights, and the encoder that was used for x2 is left without the update. So we only update the encoder through which x1 was passed. To give you some more details how this works, let's look into the source code. So really this is the best way to fully understand how SimSiam works, and this is just a pseudocode which is PyTorch-like. So we take an example, input image x, we apply the augmentations to compute the views of this image, meaning x sub 1, x sub 2. We pass these views from the same encoder f through the same encoder f to get representations z. Then we pass the representation z through the projection head h to obtain predictions p sub 1 and p sub 2. Then we compute the loss. Note that the loss has two parts. The first part of the loss is computed between predictions 1 for p1 and the representation 2 z2. The second part of the loss is computed between the prediction 2, meaning p sub 2, and the first representation z sub 1. Then we do the standard backward pass and compute the update for the encoder f and projection head h. Let us look into the negative cosine score. So we take the prediction p and the representation z as the inputs to the part of the loss which is in the negative cosine. We stop the gradient by detaching z, the representation, and we normalize prediction p and representation z. Then we compute the linear product between p and z. DINO is a SOTA, state-of-the-art encoder, and it stands for the self-distillation with no labels. So DINO trains student and teacher encoders, both with the same architecture, but different parameters. And here the teacher is updated with an exponential moving average of the student encoder. So different random transformations of the same image are generated and passed through both the student and the teacher encoders. The student is provided with smaller crops of the inputs than the teacher, which forces the student to generate representations that restore the parts of the initial image. The training objective is to minimize the cross-entropy loss between representations from teacher and student. Similarly to SimSiam, DINO also uses the stop gradient operation, and it also leverages the centering and sharpening in the softmax operation. By now, you might think that all the self-supervised learning frameworks operate in the Siamese-like architecture. However, this is not the case. Another popular architecture for self-supervised learning is based on so-called autoencoders, and in this case we are dealing with masked autoencoder, in short MAE. The main objective is to reconstruct a masked image through a bottleneck in the middle that is a small dimensional representation. To provide more details, during the training of the MAE encoder, a large random subset of input image is masked out. The encoder is applied to the small subset of the visible input image, and then in the middle we arrive at a small representation after the encoder part. Then the small decoder reconstructs the original image in pixels starting from this low-dimensional representation vector. After this training, the decoder is discarded and the teacher is applied to uncorrupted images for recognition tasks. After the introduction to SSL, self-supervised learning, now we will discuss how to obtain stolen encoders from a given victim encoder. First, we will show how to extract SSL encoders, and then we will discuss potential defenses. So the framework of the encoder extraction is inspired by Siamese networks. For an input query, here represented as an image of a Welsh corgi dog, we generate two augmentations by applying horizontal flip and grayscale transformation. Then we query the victim encoder with the first augmentation and our stolen copy with the second augmentation of this input image. To steal the victim encoder, we train the stolen encoder to minimize the loss between representations obtained from the victim encoder, y sub 1, shown in blue, and the representations from our stolen copy, y sub 2, shown in red. So now let's focus on the loss function used for stealing encoders. We also apply contrastive loss functions to steal the encoders. In the representation space, before stealing, the positive pairs from the victim and stolen encoders are far from each other. After stealing, the positive pairs are close to each other. Thus, stolen encoder replicates the behavior of the victim encoder. How to improve the attack? If you issue too many queries to the victim encoder, it's expensive and you can be detected. We don't need to do as many queries to the encoder as it was, for example, the case for supervised learning. The key observation is that the victim encoder returns similar representations for an image and its augmented versions. Thus, to reduce the number of queries sent to the victim encoder, you can query it only once. Then we augment images many times and query our stolen copy. After the training of the stolen copy, all the representations for the augmented image should be close to each other, to the given anchor representation from the victim. The selection of the loss function is one of the most important parameters for stealing encoders. We compared standard losses as well as modern batch contrastive losses. The standard loss, like mean squared error, is used to directly minimize distances between representations from the victim and stolen copy. Modern batch contrastive losses, like soft nearest neighbors, compare not only positive but also negative pair samples. We observe that, first, the contrastive losses perform the best for training and stealing the encoders. The general trend is that the best loss for stealing a given model should be roughly the same as the loss used to train this model that we want to steal. Our second observation is that the number of stealing queries can be less than 1/5 of the number of training data points. Taking into account that the stealing of SSL, self-supervised learning encoders, is an expensive process, if we can decrease this cost by more than 80%, then it is a substantial cost reduction. In supervised models, it is simple to measure the similarity between the predictions. So we use, for example, fidelity of the extraction, or just analyze what is the performance of a given stolen model. However, for self-supervised models, we were the first to measure the quality of the stolen encoders directly from representations. So here the idea is that we don't have to create a downstream task on a given encoder, but we directly measure the stolen encoder quality by comparing representations between the stolen copy and the victim encoder. So, to measure the quality of stolen encoders, we proposed two metrics. The first metric computes the mutual information between the victim encoder and its stolen copy. So here we denote the mutual information and it's computed as I, and it's computed as the entropy, which we denote as H. So we compute the mutual information between stolen and victim encoders by first computing the entropy for the stolen encoder, so H of F sub S, given dataset D, so on which we trained the stolen copy. We add entropy of the victim encoder, which was also trained using dataset D, and we subtract from that the joint entropy between encoders S and V, so stolen encoder, and the victim encoder. The second metric simply computes the cosine similarity score between the representations from the victim and stolen copies. We observe that both metrics provide a reliable measure of encoder similarity as they increase consistently with more queries used for stealing the encoders. So in this table, on the bottom of the slide, we showed in the first row the number of queries used to steal an encoder, which was trained on ImageNet, and then in the second row we show the scores for the mutual information, and the last row is score for the consistency score. So the more queries we issue against the victim encoder, so the more faithful copy of the victim we obtain on our end as an attacker, also the higher the score, either mutual information score or the consistency score. Having discussed how to steal encoders, let us now consider defense methods. The watermarking based defenses, for example, embed a unique task into the encoder, which marks the encoder as our property. If we can prove that the stolen encoder also has our unique property, then we can detect a theft. During standard training of encoders, we provide as inputs images and train the encoder to generate high-dimensional representations. So this is the standard way how we train the encoders. Now, if we want to watermark the encoder, then for watermarking, we embed, in this case, the rotation task into encoders during training. As an example, the task is a binary classification where we have to classify if a given image is rotated between 0 and 180 degrees or between 180 and 360 degrees. To implement the watermark, we add the additional fully connected layer on the representations. Whenever we tune the parameters of the rotation task, we also adapt all the other weights in the encoder. As a result, the watermark encoder and its stolen copy return not only embeddings, but also the correct rotation range. So if encoder is not watermark, then encoder cannot really predict correctly what is the rotation of a given input. However, with this additional task embedded into the encoder, we can also have this additional feature which is hidden within the encoder, and it can act as the watermark. Let's analyze the transferability of the rotation watermark. In the graph, we show the watermark success rate, whether the rotation range was classified correctly or not. And this is on the y-axis as a function on the x-axis of the number of queries used for stealing. We observe that for the legitimately trained model, the watermark task achieves near random accuracy of 50%, and this is denoted as a dashed black line at the bottom of the graph. On the other hand, for a stolen encoder, the more queries are used for the extraction, the higher transfer of the watermark. This holds across many loss functions used for stealing. However, there are many drawbacks of watermarking. First, watermarking requires retraining or fine-tuning the large encoders, which is a lot of effort. Second, the adaptive attacker can use different extraction methods to lower the transfer of the watermarks from the victim to stolen encoders. Finally, there exist many methods to remove watermarks. For example, in the case of the rotation watermark, an adversary can obfuscate the representations to full detection of the watermark. Some researchers showed that we can remove watermarks via, for example, model compression or model pruning. To tackle the problems with watermarking, we created a new detection method which we call Dataset inference for self-supervised models. In this detection method, the dataset used for training serves as the signature. Let me first give you an intuition behind our solution. So in the middle, we represent train and test data points that come from the same distribution. For independent encoders on the right-hand side, the representations h sub train and h sub test are IID and not distinguishable. However, for victim or stolen encoders, since we train the encoders on the train set, in the case of the victim it's directly, in the case of the stolen copy it's indirectly through the stealing process. then for these both encoders, the corresponding representations H sub train and H sub test, they induce different distributions. For the resolution of the ownership of a given encoder, we assume that we, as a defender, have access to our training and test data, as well as the query access to a suspect encoder. Train and test data points come from the same distribution. The first step is to train a meta model. In this case, we train a Gaussian mixture model to estimate the distribution of representations. We use part of the training set to do so. First, let us discuss a bit more what is this Gaussian mixture model and how can it give us the likelihood of given representations. So, in our defense, we train this Gaussian mixture model, in short GMM, to model the distribution of representation. GMMs is a universal approximators of densities. So GMMs are the probability. So GMMs gives us the densities, which are probabilities of data points. We can to be more precise, actually these are the likelihoods. We compare what are probabilities of two representations occurring if we train this GMM on our representation space. So GMM is completely determined by the parameters of its individual Gaussian components, parameterized by mean and the covariance matrix, or in a single dimension, the covariance matrix is just the sigma, standard deviation. A fitted GMM can give an estimate of the log likelihoods of data points. So this is also called so-called estimated density. The example shows a Gaussian mixture of three normal distributions in a single dimension. One hint that data might follow a mixture model is that the data looks multimodal, which means that there is more than one peak in the distribution of the data. In this case, we have actually three peaks, and trying to fit a multimodal distribution with a unimodal, meaning one model, let's say Gaussian model, this generally gives a poor performance. Since many simple distributions are unimodal, an obvious way to model a multimodal distribution is to assume that it is some form of mixture of many unimodal Gaussian distributions, which of course makes intuitive sense. Furthermore, GMMs maintain many of the theoretical and computational benefits of Gaussian models, making them practical for efficiently modeling very large datasets. So in this example, in this slide, we do not model such distribution by a single Gaussian, but we try to fit a few of them, in this case the three Gaussian distributions that perform the best for this overall multimodal distribution. So this is how the Gaussian mixture model is defined. So it is a parameterized function, p of x, and this is parameterized by two types of values. The first is the mixture component. This is actually an important part of this mixture of Gaussians. So this is just component weight expressed as phi sub I. This is just the weight for each Gaussian. The second type of components is these components for Gaussians, which are just the mean values and variances or covariances. This is actually standard deviation sigma. The second equation shows the standard Gaussian probability distribution function, and the component weights phi sub I add up to 1. So this is just if we model single-dimensional distribution. However, in our defense, actually we need to model the log likelihoods of the representations, which are of course multidimensional vectors. So now for this case, for our defense, we need to use the multivariate Gaussian distribution. So we compute the relative likelihood of a representation, which is multidimensional, and then we change here from the single variable x to a vector x with this upper arrow to the right. And we use the multivariate normal distribution, so we just replace this second line with the Gaussian mixture distribution, Gaussian distribution for multivariate case, and then we here have the Gaussian, which is parameterized by the mean vector, mu vector, and replace the sigma, standard deviation, with the covariance matrix expressed here as the sum symbol of sub I. And again, we want to ensure that if we have this model with mixture of Gaussians, this mixture is parameterized by phi sub I, so we just assign some weight to each component, each Gaussian, multivariate Gaussian in this case, and these weights, phi sub I, they have to add up to 1. So we use Gaussian mixture model, GMM, here in 2 dimensions to model the distribution of representations. So we train GMMs on part of the training data and then apply them to measure the log likelihood of representations of the remaining training data versus some test data. For the victim encoder or its stolen copies, the log likelihoods computed from this mixture of Gaussian models, GMMs, for the training data points is significantly higher than the one for the test data points. On the other hand, the log likelihood is similar for train and test data when computed on representations from an independent encoder. So, to resolve the ownership, we compare the log likelihoods for the train versus test sets. In the case when the log likelihood is much larger for the train set, we mark the tested encoder, also called suspect encoder, as being stolen. And then what I want to emphasize is that really to model these representations, to model the densities, actually we need this Gaussian mixture model. Otherwise, if there is almost no difference in the log likelihoods between the train and the test sets, then such an encoder is marked as independent. In our work, we use an arbitrator. So this is a third trusted party, for example, it can be a court. The advantage of using the arbitrator instead of querying the potentially stolen encoder is that the victim does not reveal the train set to the adversary if we use the arbitrator. And then what are the consequences is that if the victim would just query some suspect encoder, who is for example adversary could claim ownership of this data because of collecting the data from the queries, from the victim, and then, for example, further fine-tuning or retraining the encoder on the respective received inputs. So this is why the arbitrator was introduced to make sure that in the court cases, this can be easily resolved. I mean, that this ownership, who a given encoder belongs to. How do we quantify if the representations are equal? So this is an important question, and we address that by harnessing statistical testing. Concretely, to verify the ownership, we use a statistical t-test. For this t-test, the null hypothesis is that there is no difference between the log likelihoods for the train set versus the test sets. We set the threshold for the p-value to be 5%. If the p-value is below 5%, then the encoder is either the victim or stolen. Otherwise, the t-test is inconclusive and the suspect encoder is marked as being independent, meaning not stolen. Here in the table, we present our empirical evaluation. We observe that our test correctly assigns the p-value below the threshold of 5% for a stolen encoder, while the independent encoder has a p-value 10 times higher than the threshold of 5%, meaning that we don't have false positives. So we never can accuse somebody that this encoder was stolen, even though the given party trained the encoder independently, meaning on their own, using their own data. And then what is also very important here is that for the victim encoder, this is the sanity check. If we also compute this p-value, the p-value is almost 0, which means that indeed this encoder was trained on the train set. Let us consider an adaptive attacker against our defense. So the adaptive attacker steals the encoder and then obfuscates the gradients to fool the arbitrator and avoid theft detection. However, because the adversary obfuscates the representations from the training and the test sets in the same way, the arbitrator is still able to detect a significant difference between them. So, what are the potential obfuscations that an adaptive adversary can apply? An attacker might obfuscate the representations, for example, by shuffling the elements in the representations. This is done by moving the, let's say, first element from the initial representation to the second position, and then we move the element from second position to the first position, and so forth and so on and so forth. An adversary might also add a constant value within the representations, or just pad them, for example, with 0 values. And still, for these cases where we, for example, have this additional obfuscation, adding the elements within the representations or padding them, the p-value is still much below the threshold of 5%, which means that even if we have this obfuscation, we still correctly classify the encoder as being stolen. Adversary might also apply other transformations, such as linear transformations of offer transformations. So in the linear transformations, we just apply some multiplicative value, for example, multiply all the elements by 2, or we multiply by some constant and add some constant, which is affine transformation. And there are many different other ways how to transform the representations. We can also, for example, intermingle these different augmentations. So, for example, apply shuffle, and then after shuffle apply linear transformation. So what we observe is that despite all of the possible augmentations, all the possible modifications of the outputs, our method assigns p-values for these stolen encoders that are below the threshold of 5%. Thus, this implies that our method is robust to such obfuscations, and still, for independent encoder, where there are no obfuscations, this encoder has the assigned value way below 5%, which means that we don't have this false positive. And a very important aspect is that these augmentations, transformations applied to the representations, they don't actually lower the performance of the encoder on downstream tasks. Now the question is, what are the drawbacks of the dataset inference method? First of all, it only works post hoc, meaning after an encoder was stolen. Actually, we would like to detect the theft while it is happening, thus prevent it. The second drawback is that dataset inference requires private training and the test data. However, very often the data used to train the encoders is public. For instance, the training of the GPT-3 model was done on the scrapes from the internet. We also showed that it is possible to run dataset inference when only a small subset of the training data is private, so-called a seed. However, the method's performance, meaning the detection of the theft, degrades the smaller the private training set of the encoder. To tackle the problems with ownership resolution, we created a novel active defenses against stealing SSL encoders. So the goal in active defenses is to increase the attack cost for malicious users, but the question is, how can we identify these malicious users? To detect a malicious user, we estimate information leakage for a given user. By definition, an adversary wants to extract as much information from the model as possible. Users who incur much more information from the API than legitimate users have to pay much more for access to the API. For the supervised models, we easily can estimate information leakage, for example, by computing the entropy on the softmax outputs or using methods from differential privacy. However, in the case of the encoders, which return high-dimensional vectors, doing that actually is non-trivial. So we have to come up with new ideas how to measure information leakage from the encoders. So we design active defenses for SSL encoders. We analyze the coverage of the representation space. So here this graph on the left-hand side actually represents what are the representation spaces covered by the queries to the API. So we observe that for legitimate users, the queries come from a single downstream task, from a single part of the representation space. So we consider that standard users, for example, have tasks like SVHN, CIFAR10, STL10, FMNIST, and the queries from such subset of the large data, these subsets occupy a small part of the representation space. We call it a single region. However, the adversaries on the right-hand side do not want to steal only a subset of the encoder, but they want to steal the whole encoder functionality. Thus, the representations returned for the stealing queries cover the whole representation space. The attackers must use a diverse set of queries to achieve that. They have to query the entire representation space to succeed, and this difference between legitimate users and attackers is the foundation on top of which we build the active defenses against stealing self-supervised encoders. So just to recap, this main idea is that these users who are standard users, legitimate users, they just query a small subset of the representation space. So let's say they have CIFAR10 and they query just a small green part of the whole representation space. However, attackers, they have to cover the whole representation space. The main idea is that we can divide the representation space into buckets and use local sensitive hashing. So this is to really be able to estimate what is this coverage of the representation space. If queries come from the small subset of the whole possible data, then these queries cover a small region of the representation space. And very likely these representations from this small subset of queries, they fall into the same bucket and occupy a very small number of buckets. So for such legitimate users, the querying of our API is cheap. On the other hand, if adversary queries the API, they want to extract the whole encoder, and their queries occupy many such buckets. In this case, they have to pay much more for their queries. We increase the cost of the queries to the encoder as the queries come and occupy more and more of the latent representation space. The final goal is to make the stealing of the encoders to be costly for attackers. How do we do it in more details? To measure the coverage of the latent space, we use the local sensitive hashing, abbreviated as LSH. LSH divides the latent space into hash buckets. First, we take the representations from the incoming queries and we apply a hashing function to the representations. Then, as in the standard hashing algorithms, these hashed representations are mapped into hash buckets. Standard cryptographic hash functions are characterized by high dispersion such that hash collisions are minimized. In contrast, LSH hashes similar data points into the same or proximal hash buckets, which is the property that we desire for the measure of the representation space coverage. We present the fraction of buckets occupied by representations of different data sets as a function of the number of queries posed to the SSL model. We observe that representations for the downstream datasets, such as FashionMNIST, SVHN, and CIFAR10, occupy much smaller fraction of buckets than representations from the complex ImageNet dataset. So here we have on the x-axis number of queries issued against the API. So we have 0, 10,000, 20,000, and so on and so forth. And on the y-axis we have number of occupied buckets that we computed, that we estimated as being occupied by the incoming queries and their corresponding representations. So we observe that for legitimate users who query just small subset of this representation space, they occupy also a very small number of buckets. However, if adversaries query from diverse datasets like ImageNet and they really want to steal the encoder, then they occupy much more buckets. In the previous slide, the underlying SSL encoder was trained on the ImageNet dataset. We further show how the complexity of the querying dataset influences the success of the attack. Starting from the dotted blue line for the easiest dataset, here this is easiest one being CIFAR10, we see that these queries occupy a relatively small fraction of these buckets. When we move to the more complex datasets such as ImageNet, in this case ImageNet just subset for the dogs, where we select from the ImageNet dataset only these images that contain a dog. Then we further increase the query complexity and more buckets are occupied. Finally, even if our dataset is different than the dataset used to train the encoder, in this case we use the complex Lion dataset, the effect is the same as for ImageNet. So due to the complexity of the queries from Lion, we occupy more buckets and have a potentially a higher performance of the stolen encoder when using the Lion dataset. In this case, the legitimate users would behave as the ones who query with CIFAR10 or with dog classes from ImageNet, whereas the attacker would use ImageNet or Lion to steal the whole encoder. And this gap between these two separate types of queries, between these, for example, simple queries like CIFAR10 or queries that just cover dogs, versus these complex queries from the whole dataset like Lion, this gap between this occupied number of buckets helps us to distinguish between the attackers versus legitimate users. Once we have the estimated coverage of the representation space, we map it to cost of a query. We want the cost to be negligible for legitimate users and very high for attackers that want to steal the encoder. For example, when we focus on the blue line, we allow a user to cover up to 30% of the representation space, where the user can cover 20% without paying much cost. This is this flat part of the blue line from 0 to 20%. And then after that, the cost grows exponentially with a higher percentage of the occupied buckets. In this active defense, the cost is expressed as the amount of added noise to the output representations. The more the representation space is covered, the more noise we add to the output representations to lower their quality and make it much harder for the attacker to steal the encoder. So just to give you more details, so x-axis represents a percentage of buckets occupied, as we showed in the previous slide, and the y-axis represents standard deviation of the added noise. This is the sigma value for the added noise to the output representations. And then if we set the sigma to be 0.5, for most of these downstream tasks like CIFAR10 or ImageNet or Fashion MNIST, already the representations are of lower quality and the downstream task performance suffers and is close to the random classification. If we consider the sigma being 1.0, this is very high amount of noise added to representations, so this is really where any of the advantage of representations drops to 0, meaning that they are not helpful to create any downstream tasks, and at the same time they disable the possibility for the attacker to steal the encoder. To summarize this part of the active defense framework, first, the API calculates representations for the incoming queries. Second, we instantiate the coverage estimation with local sensitive hashing and approximate the covered space as the fraction of hash buckets occupied. Third, we calibrate this cost by adding noise to the representations according to the computed average. So up to now we analyzed attackers that have just a single account. However, we also consider sybil attacks where an adversary generates many fake accounts to query the model from all of them. Here, per account, the adversary is indistinguishable from an attacker. So the question is how we can deal with such smart adversaries. So to prevent sybil adversaries from eluding our defense, we also individually transform each user's representations. So for each user that has an account with our encoder and queries our encoder, we generate a random set of transformations. So these are transformations such as affine transformation or shuffling of the representations. This prevents the adversary from directly mapping and aggregating representations over multiple accounts to create their stolen encoder copy. As an example, the pad and shuffle transformations add constant values within the representations and shuffle the elements. We observe that our defense lowers the quality of representations for adversaries so that their performance is even more than 5x worse than for legitimate users. So here in this table, what we assume is that in the first row, we don't have our defense used, meaning none. And in the second row, we have this active defense called bugs for buckets, or in short, B4B, activated. And here we compare the performance of the encoder, which is either protected or none, or on 4 different downstream tasks. So we use FR10 task, STL10, SVHN, and fashion MNIST. And then what we observe is that the performance of the downstream tasks without our defense, for example, is 68.1% on CFR10. However, once we add our defense and then adversary steals the encoder, then the performance on this task is only roughly 12%, which means that our defense really prevents the attack. If the encoder is not protected, adversary has obtained much higher quality encoder, in this case 68.1% on CFR10, and with our defense in place, the performance of the stolen encoder is much lower. So this clearly shows that our defense, B4B, can actively prevent the attack and makes this impossible for the attacker to steal a high quality encoder. So let me now summarize the main points on stealing, attacks, and defenses for self-supervised learning models. So recent attacks on the SSL models show that high-quality models can be extracted at the fraction of the cost of creating the victim encoders. The stolen models can be used as reconnaissance prior to mounting other attacks, for example, adversarial examples, and we'll talk about them in the next lecture. So at the very beginning, in the second lecture, in the previous lecture, actually we showed that there is an example of that researchers trained ResNet50 encoder, and then if you want to train the encoder from scratch, then the cost is roughly $5,000. However, if we want to just steal the encoder from the already pre-trained one, then the cost drops to only roughly $72. So the incentive for the attackers is really high. And then how really this stealing works. So we showed that the main components of this stealing of the encoders are based on Siamese networks, so the same kind of framework as is used for self-supervised learning and reusable representations. So in general, we showed that these attacks are very effective, and then we send the queries to the encoder to obtain answers. The query, as well as many of its augmentations, are also passed through the stolen copy and then backpropagated through the stolen model, so that the representations for all the augmentations match the representations returned by the victim SSL encoder. So the main point is to really ensure that we can reuse the representations obtained from the victim many times using many different augmentations of the initial query. So essentially, what is really happening is that we want to some extent, imitate how we train the encoders, but then leverage the specificities of SSL encoders to obtain very high performance stealing process. And defending SSL encoders actually is non-trivial, as we showed in many of these examples. So we started from showing that watermarking SSL models is not effective. There are possible ways how to do it. In our case, we just show that we can, for example, embed some secret task into the encoder. In our case, the task was just to rotate the given image and then also force the encoder to predict what's the rotation range. Instead of watermarking, we also propose a better method which uses the training data, which we assume to be private, as the signature for the given encoder. So this defense based on dataset is effective. We showed that given the assumptions, it can also, for example, be robust against obfuscations. However, the problem with ownership resolution is that these methods work post hoc, meaning after the model was stolen. And our main goal is really to prevent the stealing as it is happening. So finally, instead of waiting until the model is stolen, we proposed active defenses that do not lower the quality of output for legitimate users. So our defense, called B4B, from bugs for buckets, make model extraction more difficult. So this defense relies on the observation that representations returned to adversaries cover a significantly larger fraction of their embedding space than representations for legitimate users. With that, we can create defenses that can be used during the operation of the encoder when we expose the encoder by public API. So thank you for the attention, and then you can also consult some of these references. These are very recent papers that were published about stealing and defending encoders, and then I hope that you can here find more information about the specific aspects of the discussed defenses and attacks, and delve deeper into the topic. And thank you. With that, thank you for your attention, and see you next time.